Hi everyone, I welcome you all in the next lecture of quantum chemistry. So, in today's lecture, I'll be talking about some state and state space. So, in quantum mechanics, unlike classical mechanics, we study the phenomena that are not considered in classical physics. Therefore, we need to understand a different kind of language to describe the quantum system, and based on this language we can develop a theoretical framework, and from that framework we can drive uh, meaningful results. So in quantum mechanics, a state of a system represents the complete physical description of the system at a given instant of time. So if I want to define the state for a quantum mechanical system, so it can be written as it represents the complete physical description of that system at a given instant of time, right? So mathematically the state of quantum mechanical system can be represented as a wave function. This is called as the psi of xt, and this is called as the wave function. And obviously this represents the instantaneous state of the system. That's why this will be a function of both x and t. Psi will be a function of both space as well as the time. Okay, and so all measurable informations that about the system. So let's say if all measurable information about the system, that is also called as observable, that we'll discuss in later on. So all measurable information about the system, that can be your linear momentum, energy, probability density, so and so forth, etc., is considered or is constrained in the wave function, right? Now, so coming to the state space, it's also very important. Coming to the state space, so this is some kind of theoretical thing that you have to understand here, and then later on we'll let you know while relating this thing so with the linear algebra. So it is the collection of all possible states that a system can have. So it is a collection of all possible states that a system can have. So mathematically what happens, we can mathematically it is a linear vector space, and that is also called as the Hilbert space, right? This is also called as the Hilbert space, formed by all allowed wave function. So right, so let's say if psi1 and psi2 are two wave function, that is your two valid states, right? Then we can say that A psi 1 plus B psi 2, that will be your valid state, valid states, and this is also called as the superposition principle. This is called as the right. So here you can see that each element of this space represent a possible physical state. So each element of this space represent a possible physical state. Okay, so now let's say, since we are talking about a state space, so let's say psi 1x, psi 2x, psi 3x, so on and so forth, are the wave function, right? Are the wave function. So let's say, so in order to represent the wave function, it's very important to understand these things. So PM Dirac has significantly contributed for the invention of this state wave function, and that's why he has given a notation to represent a wave function. So let's say this wave function can be denoted as, let's say, like that, psi 1, and that notation is called as the ket notation. And in another way, you can also represent this as like psi 1, and that is called as the bra notation. So this bra and ket notation together constitutes a bracket notation, for this wave function. So like in linear algebra, what happened, we states that there is a unit vector in linear algebra, and this unit vector is represented as, let's say, E cap, right? So similarly in wave function also, in quantum mechanics, the wave function, we call it as normalized wave function. We call it as normalized wave function, and when we call it as a normalized wave function, then when norm will be equals to 1, and we'll let you know how to calculate the norm of wave function. So let's say we have a psi x, that is a wave function. Psi x is a wave function. So if I want to calculate, let's say, minus infinity to infinity, and if we perform psi star x and psi x dx, and if this value is 1, then it will be called as normalized wave function. And what is the norm? So a square root of these things. So basically, if I want to calculate the norms, or if I want to calculate, let's say, psi of x and psi of x, that is the scalar product of psi, that will be equals to minus infinity to infinity, and then the complex conjugate of psi x, and then there will be a psi x and dx. So once you calculate these things, and this is the square root of norms, right? And if it is equals to 1, then we are calling it as a normalized wave function, right? So let's say in linear algebra, what happens in linear algebra, if we have two vector a vector and b vector, and if I want to denote the scalar product of vector a and b, so you can write this like that. This is called as the scalar product of vector a and b. Is that clear? Okay, so this is called as a scalar product. And if I take a scalar product of vector a with respect to vector a, so we will be getting the square of mod. Is that clear? And since a scalar product of a vector, here we are taking a scalar product of a vector by itself, and this gives you the square of the magnitude. So if it will be equals to 1, then what will happen? The vector a vector will be called as the unit vector, right? But similarly, if we talk about in terms of wave function, because we have to relate linear algebra with the wave quantum mechanics, and then that it will be very easy. So if we have two wave function, let's say psi 1x and your psi 2x are two wave function, right? And if I want to calculate the scalar product of psi 1x and psi 2x, so as I have told you already, so that is minus infinity to infinity, integral over minus infinity to infinity. So you have to take complex conjugate of first wave function psi 1 star x, and then another wave function psi 2x will be as it is, and then integral over dx, right? Or if I take the scalar product of psi 1 with respect to psi 1, right? So it will be equals to minus infinity to infinity. Or if psi is our wave function, let's say only psi is our wave function, and if I take a scalar product of psi with respect to psi, so it will be equals to psi star and psi dx. Is that clear? And that integral limit will go from minus infinity to infinity, and this is the square of magnitude, right? So this is your and this is, that means root of norm, right? And that is the root of norm. So similarly, let's say if we take a scalar product of a vector and b vector, and if it is equals to 0, then a vector will be orthogonal to vector b. Vector a will be orthogonal to vector b. Is that clear? And similarly, in wave function as well, if psi 1, a scalar product of psi 1 and psi 2, that will be equals to 0. So the wave function psi 1 and psi 2 orthogonal, psi 1 and psi 2 will be called as the orthogonal wave function. Is that clear? Great. So I'll stop the lecture here. From the next class onwards, I'll be talking about basis in Cartesian coordinate system, and then we'll start discussion. Then I'll extend that concept of basis in Cartesian coordinate system linear algebra to the quantum mechanical wave function. Okay. Thank you all for attending the lecture. See you in the next lecture.